This is the beginning of Chapter 3, 3.1 on frames of reference, which is still dealing with Unit 1. Chapter 3, we're going to be talking a little bit more about circular motion and some of the properties and forces that exist here. But we first must talk a little bit about our frames of reference. And we must recall our law of inertia from Newton. And that is Newton's first law. And we remember that Newton's first law of inertia tells us that there is no net force acting on an object. And what does that mean? No net force tells us that we have no acceleration, okay? And that in itself means no change in velocity. And due to this, when we're talking about frames of reference, we can talk about two different types of frames of reference. We could have an inertial frame of reference. An inertial frame of reference is a frame of reference that is not accelerating. And if it's not accelerating, that tells us that the law of inertia holds. So we are able to use the law of inertia. For example, when a car is traveling at a constant velocity, and a ball is thrown in the air, where does that ball land? Well, due to the law of inertia and the fact that there is no acceleration occurring or traveling at constant velocity, the ball will return exactly where it began, and that is in the passenger's hand. So we may have inertial frames of reference where our frame of reference is not accelerating. We might also have non-inertial frame of reference. And this is a frame of reference that is accelerating. And if our frame of reference is accelerating, what does this tell us? That tells us the law of inertia does not hold. So how do we observe these non-inertial frames of reference? What we have done in physics in order to analyze motion of non-inertial forces or frames of reference is create fictitious forces. And as this is named, you can probably hypothesize what this actually means. fictitious forces are non-existent forces. That explains the motion of objects in non-inertial frames. So these forces are evident to us as observers, but they do not actually exist. Why do we have frames of reference? Frames of reference exist so that we can explain the motion. This is why we have our fictitious forces. And the fictitious forces help us to solve problems dealing with non-inertial frames. For example, if a teacher suspended a small cork ball from the ceiling of a bus, and the bus accelerates at a constant rate forward, the string suspending the ball makes an angle of 10 degrees with the horizontal or with the vertical, We would like to figure out what the scalar acceleration of the bus would be. So if we picture this bus and we suspend this cork ball and it accelerates, the cork ball is actually going to be towards the back. And remember, this is actually from a non-inertial frame. And we have a 10-degree angle with the vertical. We can observe this actual motion from an inertial frame to explain this movement. And this inertial frame, we could be observing this motion from outside of the bus. And that would give us a way to create a free body diagram for this type of problem. So here I have my bus, a force of gravity that is acting in the downwards direction. And we always know that the force of gravity is mg. And we would have the tensional force acting to the right. And we have an angle with the vertical of 10 degrees. And we notice in this case we can call upwards and to the right our positive direction. And we will see right now that the only motion, the acceleration, is in the x direction. So that will come in handy when we go to solve this problem. So let us separate this problem into both an x and y component. Let us list off what we have. Let's start with the y component because our x is easy because there's only one force acting in that direction. We notice in the x, or in the y direction, we do have a tension force for the y direction. And that tension force will be given by Ft cosine of 10 degrees. Why is it cosine in this case? Because my angle is 10 degrees and Fty is on the adjacent side and Ft is at our hypotenuse. I also do have my force of gravity as we see in the y direction, which is mg. If I observe the net force in the y direction, that gives me Fty subtract the force of gravity, and because acceleration is only forward, we can assume that the net force in the y direction is 0. Therefore, Ft cosine 10 degrees minus mg is 0. Let's solve for the tension force because that will help us combine both the y and the x direction. Ft cos 10 degrees is mg. I can solve for Ft by dividing by cos 10 degrees. that has given me an equation for Ft. Because in the x direction, going back to my free body diagram, I notice that Ftx is on the opposite side of 10 degrees. So Ftx is Ft sine 10 degrees. And that my net force in the x direction is simply Ftx, and my acceleration is also in the x direction. Therefore, that is mass multiplied by acceleration. So Ft sine 10 degrees is ma. I have Ft in the x direction. We solve for Ft in the y direction to give us an equation for it. We make that substitution. So that tells me mg sine 10 degrees over cos 10 degrees is my mass times acceleration. And doing some nice manipulation of this formula, we have m's which cancel out. And we notice that we have sine 10 degrees, cos 10 degrees. Remember the trig identity from yesterday. That gives me g sine 10 over cos 10. Sine over cos is always tan. So g tan 10 degrees is my acceleration, which in this case gives us 1.73 is the acceleration. So therefore, the bus accelerates at 2 meters per second squared. We're going to call it forwards. Okay? Again, combination of both our x and y components can help us to solve for a case where you might have fictitious forces. Okay. Example 2. Let me zoom on up here. An elevator with an acceleration of 1.5 and upward acceleration of 1.5 meters per second, after which it moves at a constant acceleration. As the elevator approaches a stopping point, it undergoes downward acceleration. Calculate the apparent weight. What is the apparent weight? This is basically our normal force, and we can basically explain this as how heavy we feel. And we have the mass of this person, this passenger, at 75 kilograms. Let's determine the apparent weight, Fn, when the elevator is going in the upwards direction. So if I think about my free body diagram, we have that mass that's in our elevator at 75.0 kilograms. Upward acceleration means that my force of gravity is going to be less than my normal force. If we call up positive, it's merely net force will be Fn minus Fg, and that's our mass acceleration. And Fg is easy because we know that's mg. Therefore, Fn is ma plus mg. We make those substitutions, we can determine the normal force. After making the substitutions, punching this into your calculator, the apparent weight of this passenger is 850 newtons. Significant digits, we're good, 2 significant digits at most. There is our apparent weight in a positive acceleration. Constant velocity tells us net force is 0. If our net force is 0, that means my gravity and my normal are of equal value. So therefore, net force, Fn minus Fg, is equal to 0, and my normal force is equal to my force of gravity, so that will be 9.81 multiplied with 75.0. The apparent weight in that case will be 735.75, or two significant digits, 740 newtons. Let's look at C. Downward or negative acceleration. Yet again, this passenger has experienced a force of gravity and a normal force. I'd like to pass two examples. Up is positive. Again, I can figure out my net force. I'll have Fn minus Fg is equal to mass times acceleration. Fn, therefore, will be ma minus mg, so 75.0 times 0.9 minus 75.0 times 9.81. Which we get negative 668.25. Checking that quickly on my calculator here. Yep. So therefore, Fn is 670 newtons. Downward direction in this case, because we did call upwards positive during a the negative acceleration, which makes sense.